In this video, we'll look into how can we fine-tune LLaMA 3.1 8 billion parameter model using the free tier of Google Colab GPU. As you see here, the resources on my screen, this GPU is a T4 GPU, which is freely available. But on this GPU, the RAM resources, GPU RAM and disk are quite limited. The GPU RAM is only 15 GB. If we try to kind of do even inference using 15 GB, LLaMA 3.1 8B model doesn't work. So we'll use different tricks of quantization and we'll train a model using LoRa. And we'll see how we can fine-tune such models for amazing tasks. So today the task which I'm going to show is how to fine-tune LLaMA for text classification. By default, LLaMA model does work for text classification, and we'll see how much further its accuracy can be increased. I will suggest to kind of follow this notebook along, so I'll share it in the description of the video. We have to install certain packages. Many of these packages are available by default in Google Colab, but we'll try to install the latest version for us to work. These are a set of packages which I often use in many of my tutorials. Starting with some of the normal imports. More specifically, the model which we are going to use is 3.1 8B instruct model. Instruct version of the model is the one which is specifically tuned to follow kind of instructions with chat templates defined. And we are going to save this model kind of in a directory locally, kind of like instruct fine tune, which kind of you see here in my drive folders. First, we are going to define LoRa parameters. In general, we can have a larger side of attention dimension of LoRa, but in here, I'm only going to define 2 because of memory limitation. This is very good to test simpler ideas and concepts. But when you're going to go for, say, production level model, we definitely need to increase the complexity here. Many of these parameters can be kind of fine-tuned and we can do hyperparameter search over them, but I'm picking some reasonable numbers which work. We are going to use kind of 4-bit. So with 4-bit, we do suffer loss in accuracy numbers. However, like I said, this is a good simpler concepts replication notebook, and also kind of makes it easy for student to test in the free tier itself. Some of these numbers I have explained in some of my other tutorials on quantization. You can follow those videos. But in general, we are going to enable double quantization as well so that we can tune in the same notebook. Again, the output directory is defined kind of which points to where we are going to save the model. Optimizer to use and max steps and save steps. So generally, we should kind of tune for large number of steps. Depending on your batch sizes, each step accumulates a particular number of gradients for update. Max step is 100. It's going to take more than an hour or so in this notebook to run. In your case, you can play with more number of steps, but with 100 steps, you will see a reasonable performance gain happening. We are saving the model every 8 steps, and this is also the number of steps. We'll also do evaluation on the evaluation data set, and we'll also kind of save the checkpoint after 8 steps. Now, SFT parameters actually kind of this is kind of where we want to give the maximum sequence length which model can expect. Since these are news articles which we're going to use, we'll look at the data set in a few minutes. So I fixed it smaller. Also smaller because we have a limited memory. Larger context length can be trained on very large GPU resources. Then this bits and bytes config is the one which I often use in my tutorials for quantization, kind of configuration, and then loading the model later on. You have to add your Hugging Face token if your model kind of LLaMA 8B is not saved locally, so it will be able to download that model from the Hugging Face. So in my case, I had downloaded it earlier, so it just loads the charts. Definitely, these chart, there are 4 charts which roughly kind of are more than 16 GB or so on their own. We are going with the LLaMA tokenizer, and we have to specify pad tokens and all. You can see in the LLaMA config of the tokenizer, some of these tokens are not specified, so it's reasonable to pick some numbers. This is the function which does the inference. Again, we are trying to go without sampling and trying to say that a model can stop early. The data set I'm going to use today is the news data set. So the data set is here. This is the data set which has around, I think, 100K or so training rows. For example, these are the real news articles, and we are going to classify into 4 different categories like world, sports, business, and science or tech. And these all kind of are gathered from the real news sources. And they're kind of good data set for kind of research purpose or data mining, clustering, classification, and so on. Also openly available on Hugging Face. So we downloaded this data set, and these are the 4 labels like I've defined here. There are roughly 120K examples, and news kind of looks like, for example, some news on India warning US on arms sales, and these are kind of some real news articles. And when you look at the classification of this news, its label is 0. Basically, it's classified into the world. It's not a sports, business, or science tech category. We are going to convert this data set to chat template format. So with chat template, we are going to define different roles, system and user. And using these roles, kind of the model will know that what is the goal. For example, the system role kind of defines that you have to classify news into these 4 categories. And I'm also giving it instruction that only output the news classification and so on. When the user actually is where the real news text goes into. And finally, we are ending it that we have to output the news classification. After we run this, you see this is how the sample dataset transformation occurs. For example, the earlier news article which we saw comes here, but before that there's a system kind of things, and it's enclosed within the start header ID and header ID, and finally the label is assigned as well. So this is the format where we are going to further fine tune the instruction model to follow some specific instructions, some specific kind of prompts. And I'm going to take majority of the data for training, and the test is going to have a very small number. That's kind of what we are doing here. Specifically, you will see the training has more than 100 kind of 19K data sets, and test has only 240 samples. So this is a test we're going to measure the accuracy of the model. Further, just you can look at the training kind of a sample, how it looks like, and also the input text of it, what it looks like. To measure the accuracy before we fine tune, I'm going to pick sample 200 from the test 240. We are just going to take first 200, and in this message, I'm again taking the tokenized data, running inference on the model. We are going to see if we correctly classify or not. We are going to use a real label, and we are going to see what the model classified. In this case, a model output comes after assistant, or comes after like the new classification. Like this is a thing added in the input to the model itself. We're going to take the model output, we're going to remove some new line or some spaces in it, and we're going to see if the label exactly matched. And in this case, when the label matched, we're going to say it's classified correctly, otherwise not. When it doesn't classify correctly, that's when I'm outputting it. So our assumption is model in general will do good, even the out-of-box model. So this is where large language models can be directly used as text classifiers based on just prompts. And you can see this actually to some extent works. Like the cases where it's failing is it's predicting, for example, it to be business, but it was a science tech, so I'm outputting false because it didn't correctly classify. So many of these cases do exist. Overall, sometimes it does output more things, like after we remove it's actually outputting sports, but it says I don't agree with this classification and so on. Actually, the real answer was the world. And so out of 200, it actually accurately classified 75% of the time out of box, which is a very good news actually. Now we kind of further take the tokenized data set which we had, and this is kind of the LoRa configuration which I'm going to define, and our training argument. So all of these things you can go in detail by following this class. Most important things are we are going to evaluate based on the steps, our learning rates, and some kind of important things kind of shown here, a grad norm, we are fixing it. The warm-up ratio, it doesn't make any sense because we're only going for 100 steps. But in reality, when you're going for, say, 1,000+ steps, you can fix this to a reasonable good number. And then our SFT trainer. This is the main thing where magic happens. We're going to fine tune. We have the training data set, we have the evaluation data set. You saw the training data set is 119K or so examples. Test data set is only 240 examples, and we are going to train it. Remember, this training is going to run this free trial of Google Colab itself. So it's going to take some time. Once we train it, kind of this is how the final output kind of looks like for this model. It kind of shows that what happens, and let me show you. We are going to save every 8 steps. It's going to show us the training loss. Important thing to note is training loss is decreasing over time. Validation loss are actually the test samples. We are just monitoring the validation loss. Remember, these examples we are not going to use to fine tune the model, just trying to see that actually model do learn, and validation loss also goes on decreasing. Finally, after the 100 step, we take the best model, the 100 steps model itself. We have saved all other checkpoints here as well. Why we are saving the checkpoints? One thing is that when you're monitoring validation loss, which you're interested in, after a certain point, validation loss may not decrease or start increasing. So you can take that particular checkpoint from your saved ones. In here, since we are running only for 100 steps, model actually is learning meaningfully up to 100 steps. And now let us look at how the accuracy looks like. We are again tokenizing the same data set because I had earlier removed some extra columns, but we need those columns to measure the accuracy, like those label columns and all. But the order of the data set is kept as it is. Now, we're again taking the 200 samples. Note that this tuned model do make mistakes, but accuracy now is around 78%. So you can say that we kind of get roughly 3% boost in accuracy with the 100 steps of fine tuning. One thing to note is that 3% boost is meaningful. We are not showing the test data to the model at all. This model is trained on trillions of tokens, so just showing at 100 steps actually gives reasonable boost. If you actually train it further for more and more steps and can even increase the complexity of the LoRa layers, you can expect more boost. So for more boost, my suggestion is to increase steps. Here we had limited steps because otherwise it takes a lot of time in Google Colab free trial to train. This took me more than 1 hour for this tutorial to have this notebook ready for the training happened in the free trial. And you can increase complexity of LoRa layers and which also further give boost. If you have access to more powerful GPUs, then you can remove the quantization, and that will further help the model to learn more. Because quantization does kind of hurt the performance. And remember, this is not just 8-bit quantization. We are doing double quantization in 4-bit settings. So it's more hurting the performance. And even though then again, model has gained good accuracy boost. This is all. We'll look into a few more tutorials later to do further magic with LLMs.